Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about how to model multiple continuous quantities as random variables within the same probability space. Let's get to it. When we have several random variables within the same probability space, we often call them multivariate random variables, and today we're going to focus on continuous random variables. Our goal is to model interactions between multiple uncertain continuous quantities. Let me remind you our notation for deterministic variables, which is just like this, without anything special. And then for random variables, which we write with a squiggly line on top. So these random variables are uncertain quantities that we can only describe through probabilities. Now, if you ask someone what is a random variable, and I know that, if you have seen the previous videos on discrete random variables, then continuous random variables, then multiple discrete random variables, I'm starting to sound like a broken record. I know that, but this is really important, okay? If you ask someone what is a random variable, a data scientist will tell you that it's an uncertain variable described by probabilities estimated from data, and a mathematician will give you a very different answer. They will tell you that it's a function mapping outcomes in a probability space to real numbers. And we already saw for discrete and continuous random variables how these two views are connected. We have also seen how these two views are connected for multiple discrete random variables. And today we're going to see how they are connected for multiple continuous random variables. This is really important because this is really how we deal with random variables in practice, through these probabilities that in the case of discrete random variables are encoded in the probability mass function, and in the case of continuous random variables are encoded in the cumulative distribution function or in the probability density function. But there is an underlying probability space that is only there so that things are mathematically well defined, that I want you guys to be aware of. We're not going to obsess about it, but at least we need to know why things are mathematically sound. Okay, and this is the point of this video for, multiple continuous random variables. Let us remind ourselves how this works for continuous random variables. So here I'm showing you the underlying probability space. And the idea is that we have this probability space that has a sample space, which we denote by omega. And the way we represent the random variables mathematically is as functions from this sample space to the real line. Here in particular, we have a random variable a that maps this point omega 1 to this point on the real line, this point omega 2 to this point on the real line, this point omega 3 to this point on the real line. But the way we actually describe and manipulate the random variable is not in terms of what is going on in the underlying probability space. The way we actually manipulate and describe it is in terms of the probability that it belongs to different intervals on the real line. And because of that, we need to make sure that the probability that the probability of all the outcomes that map to these intervals, so in this case, the outcomes that map to these intervals are within this circle, and the outcomes that map to that interval, the event of outcomes that map to that interval, are in this square. We need those guys to be assigned a probability by the probability measure. And this is the condition that we impose when we are defining continuous random variables. Again, this is all very mathematical. Then in practice, we are actually going to estimate these probabilities directly from data by estimating the cumulative distribution function or the probability density function of the random variable. Okay, this is a really, really quick review. If you want to know more about this, there's the video on continuous random variables. So again, a continuous random variable is a function from the sample space to the real line. And what we impose is that the probability that the random variable belongs to any interval is well defined. This is a mathematical condition which implies that the event of all outcomes mapping to that interval is inside the collection of the probability space, which means that the probability measure assigns it a probability. This is a condition that we impose when we define continuous random variables. If a continuous random variable is a valid continuous random variable, it must satisfy this condition. Again, you shouldn't worry about then having to define this probability space and this probability measure so that this holds, because in reality, all of this occurs implicitly once we estimate the probability density function or the cumulative density function from data. Okay, so we describe continuous random variables in terms of the probability that they belong to any interval. That's the bottom line here. So what about multiple continuous random variables defined on the same probability space? How can we describe these continuous quantities? And it just makes sense to consider the probability that they belong to different intervals at the same time. So for example, imagine that we're interested in two random variables. I'm going to write them here, A and B. And now I'm going to stack them as a vector. So the first entry is A, the second entry is B. Now, in order to describe the behavior of these two continuous quantities, the simultaneous behavior of these two continuous quantities, what we can ask is what is the probability that the first entry A is in a certain interval, and at the same time, the second entry B is in a certain interval. What does that mean? That means that this vector is in a rectangle, okay, where one of the coordinates is the first entry and the other coordinate is the second entry. Okay, so here, this point, this black point here, represents where the random vector ends up, this random vector that consists of the two random variables. And if we ask what is the probability that the first coordinate is in this interval and the second coordinate is in this interval, this is equivalent to saying what's the probability that the vector ends up in this rectangle. So this is just a generalization of what we do in one dimension. In one dimension, we say what's the probability that the random variable is in an interval. In multiple dimensions, we say what is the probability that the random variables are in certain intervals at the same time, or equivalently, what is the probability that the random vector composed of all of these random variables is in a rectangle, if we're considering two of them, or a hyperrectangle, if we're considering more. Okay, so now let's think about what this means. Well, we're asking, on the one hand, for the event, let's say, that the first entry is within this interval, okay? So we're interested in this event. Now we have an underlying probability space. This is the assumption. These two continuous random variables are defined on the same probability space. So let's draw it. And in particular, we're going to also draw all of the outcomes that map to this interval. That map to this interval through A. Okay, those are all the outcomes such that when we apply A, the random variable A, to those outcomes, we end up in this interval. That is well defined because A, the random variable A, is a valid continuous random variable. We impose this in the definition. That event exists, okay? And is assigned a probability by the probability measure of the probability space. Great. Now let's do the same thing for this other interval and the random variable B. So here we're interested in the event that the random variable B maps to this interval. Because it's a valid continuous random variable, when we go and we look at the sample space, and it's the same sample space because both random variables are defined on the same probability space, the event of all outcomes mapping to that interval, which here is this circle, must have a probability assigned by the probability measure. So now we have to ask ourselves, what are we really interested in? We're not interested in these events separately, right? We want to know when these two events happen at the same time, because then this 2D vector will be within the rectangle. This 2D vector is only within the rectangle if the random variable A is in this interval and the random variable B is in that interval. So what do we need in terms of these two events? Pause the video if you need to think about it for a moment. Well, we're asking about the intersection of those two events. And that's actually great because if you remember, and if you don't, go take a look at the video on probability spaces, the way we define a probability space, if two events have assigned probabilities, they belong to the collection of events of that probability space, then their intersection must also be assigned a probability. So this means that automatically, if random variable A and random variable B are valid continuous random variables within the same probability space, the probability that they belong to the rectangle is well defined. And it's going to look something like this. Okay, it's going to be the intersection between the circle and the square. If we write this in equations, we're interested in the probability that the 2D random vector is within this rectangle, that is the Cartesian product of two intervals. That is the same as saying what are the outcomes so that A of omega ends up in one of the intervals and B of omega ends up in the other interval. This is just the intersection between these two events, the events of all of the outcomes, including all the outcomes that map to one of the intervals through A, and this other event that maps through B to the other interval. The intersection must belong to the collection. It must be assigned a probability if those two random variables are valid continuous random variables. Okay? So then that means that we essentially, the way we define continuous random variables, we can immediately capture interactions between random variables. And I said this also in a previous video. That's part of the reason why we go through all of this pain of having like a probability space and then defining random variables as functions from that probability space to the real line. What happens in higher dimensions? That means more than two random variables. We have like a random vector where we stack random variables as its entries that has dimension d. Well, the idea is essentially the same. If these random variables are defined on the same probability space, then if we consider, here I'm writing Borel sets, but let's think about intervals for a moment. Imagine that you have d intervals. Then you can build a hyperrectangle of dimension d by saying what's the probability that each coordinate is within each interval. That is just the intersection, right, of all the events that map to each of the intervals separately, through each of the coordinates, through each of these x1, x2 to xd, because they're all valid random variables in the probability space. Then those events here are well defined, and their intersection, well defined in the sense that they have to be assigned a probability by the probability measure, so their intersection is also well defined. Okay. Now, why do I write Borel sets here? Borel sets are just unions of intervals, and multidimensional Borel sets are just unions of these hyperrectangles. So I forgot to say in the case of this 2D vector that because we have a well-defined probability on the rectangle, then we can build any set we want as unions of rectangles, and that's also going to have an assigned probability, and that's called a 2D Borel set. Here in D dimensions is the same thing, because the hyperrectangles are well-defined probabilities, then Borel sets, which just means unions of those hyperrectangles, are also going to have well-defined probabilities. And that's great. But of course, we are never, ever, ever, and I can't say that enough, going to actually define the probability space. The probability space is just a mathematical entity that is there so that the joint distribution of these quantities is well-defined mathematically. But we never actually explicitly construct it, and we definitely don't estimate it from data. Instead, we work with the probabilities that the random variables belong to these rectangles in the 2D case, or hyperrectangles. So how do we encode those probabilities? If you remember, in one dimension, when we had a single random variable, we had two main options, the cumulative distribution function or the probability density function. In this video, we're going to take a look at a multidimensional extension of the cumulative distribution function. In another separate video, we will talk about a generalization of the probability density function. Okay, so let's remind ourselves. The cumulative distribution function of a single random variable tells us the probability that the random variable is smaller or equal to any value on the real line. And that completely characterizes the behavior of the random variable. We can use it to compute the probability that the random variable is in any interval or any union of intervals. So what is the joint CDF of two random variables? Very naturally, it's the probability that one of them is smaller to some value on the real line, and the other one is smaller to another value on the real line at the same time. And that's why it has two arguments. It has one argument for the first random variable, another argument for the other random variable. So I don't think I have a picture of this, so I'll just draw it. Imagine that you have R2 here. Basically, we're asking the probability that, well, that was a terrible picture. The probability that we're in a region like this, where one coordinate corresponds to one random variable, like maybe A, and the other coordinate corresponds to the other random variable B. Okay, we're asking what's the probability that we're in a region like that. Okay, that's what the joint cumulative distribution function encodes. For a d-dimensional random vector or d random variables, the definition is essentially the same. It's again the intersection of these events where the first random variable is more or equal to a certain value, the second one is more equal to another value, and so on and so forth, and we encode those values in this deterministic vector x. Okay, very straightforward generalization. What are the properties of the joint CDF? And I recommend that, as we cover each of this, you stop for a moment and see if you can figure them out by yourself. What happens when we take a to minus infinity? So the easiest thing to do here, actually, just to gain some intuition, is to think of this region that I was talking about. So I'm going to draw it again. Maybe I should have just copied it, but whatever. Okay, we're interested in a region that is like that. Okay. What happens when, and basically this would be the CDF at this point. The CDF at this point tells us the probability that this 2D vector composed by the random variables A and B is in this region here. So what happens when, and let's say that this is A and this is B. What happens if we take A to minus infinity? Well, eventually that probability is going to be 0, right? So that probability is going to be 0. What happens if we take B to minus infinity? Same thing. Eventually that probability is also going to be 0. What happens if we take both of them to infinity? Then we're covering the whole plane, so that probability has to be 1 because the random vector has to end up somewhere. And now you can also think, is it possible for, and now I'm going to draw, I should have, we're going to go back so that I don't have to draw again. So we're asking, is it possible for the joint CDF at A1, B1 to be larger than at A2, B2 when A2 is greater than A1 and B2 is greater than B1? So basically, we're asking, what about the probability of being, I'm going to use another color. I don't know if that was the best color. Okay, so here, A2, B2 would be this point. This would be A2, B2, and A1, B1 would be that point. And you can clearly see that if you are smaller than A2, B2, then you're definitely also smaller than A1, B1. So the CDF at this point has to be smaller or equal to the CDF at this point. Hopefully that picture kind of makes sense, and you can obviously make this precise, essentially realizing that, I mean, I actually hate a little bit the color that I used, so let me erase a little bit here. So you can realize that this area here, so the probability that you are there the probability that you're in the red rectangle is equal to the probability that you're in the green rectangle plus the probability that you're in this region in between. Yeah, sorry for the horrible artwork here, but I hope that that was clear. All right, so what we see is that the CDF is non-decreasing in both of its entries, right? If we increase the first or the second entry, the CDF is non-decreasing, just by its definition. All right, so now let's take a look at an example This example we're going to be using to illustrate a lot of the concepts that we're going to be talking about with multiple continuous random variables. It's about a biologist that wants to figure out where an otter, an aquatic animal, is inside a lake, and the lake happens to be triangular. Okay, and the biologist doesn't know anything about the otter, so they just assume that there's the probability that the otter is anywhere on the lake is kind of the same. As we will see, this is naturally encoded by saying that the density of probability is constant on the lake. So now I'm going to show you what the joint CDF of this very, very simple 2D random vector looks like. We're not going to derive it because for that we need to use the density, and we haven't derived the density yet, but I'm just going to show you. Okay, so remember that the CDF, for example, at this point, I'm going to use red better. The CDF at this point tells us the probability that we are here. Okay, we know that the otter cannot be here, so the probability that the otter is in that part of the lake. That's why I've labeled this region B, because in B, this is always going to be some kind of rectangle, right? Wherever you are. If you want the CDF here, then that's going to be the probability that the otter is in this part of the lake. So it has a little bit of a different geometry, and so on and so forth, just in case you're wondering where these different letters come from. So now I'm going to show you the values of the joint CDF under this assumption that the density is constant. We will talk about density in the video on the joint probability density, but for now, bear with me. So this is what the joint CDF looks like. Why am I showing you this? I'm showing you this because this is an extremely simple example, and already the joint CDF looks horrible. So the reality is that in contrast to one dimension, where the CDF is actually very useful, we use it, for example, in practice, we estimate it from data to estimate quantiles, the median, things like that. In 2 dimensions or more dimensions, we very seldom actually compute the joint CDF or estimate it from data. It's an important tool because it allows us to define the joint PDF. So it's very important, that it is well defined and we use it, but it's mostly of mathematical, like its usefulness is mostly mathematical. We almost never estimate it from data. Again, look at just how it looks in these different regions. It gets really, really complicated to deal with. To illustrate that further, imagine that you're trying to estimate the probability of a rectangle just using the CDF. So here we have a rectangle. I just want to really drive this point home, where here this is B1, this is A1, this is A2, and this is B2. And now you want to compute the probability that your 2D random vector ends up inside the rectangle, and you know the joint CDF between the 2 random variables. So it's actually pretty easy to do. What are you going to do? You're going to say, well, that probability that I'm interested in is equal to the probability that the random vector is here, which is equal to the CDF at this point, F A2 B2. Now I need to subtract some stuff. So I'm going to subtract the CDF here at A1 B2. And I'm also going to subtract this CDF here at A2 B1. Okay, and I'm going to draw them maybe in different colors. So I'm subtracting this, and I'm also subtracting the probability that the random vector is here. So now the issue, if you think about it for a moment, but you will see that an issue is that I've subtracted something twice. I've subtracted the probability that the random variable is there. I've subtracted it twice. So I have to add it back. Okay. So as you can see, computing the probability that the 2 random variables are within a rectangle is relatively complicated. When you apply the joint CDF, definitely much more complicated than in 1D. You can imagine how complicated it gets when you have D random variables. You can still do it, but it's annoying, right? So here you see, this is the probability that you're smaller than A2 and B2, and we subtract these two probabilities, and then we have to add that back for the reason that I told you. This is a bit of, it's too complicated. It's a pain. We never do this. Instead, when we have continuous random variables, we just use the joint probability density that we will define and describe in a following video. Okay, so this, just obviously these probabilities, we can express them all in terms of the joint CDF. Again, very complicated. All right, so what have we learned? We have learned how to jointly model multiple continuous quantities within a probability space. And in particular, we have learned that if those continuous quantities are already defined as valid continuous random variables within that probability space, essentially we are fine. We can naturally model the interactions by considering the probabilities that they belong to hyperrectangles, rectangles in the case of 2D or hyperrectangles in the case of D dimensions. And this actually shows the potential of this probability space mathematical framework in order to capture interactions between variables. And again, this is one of the main motivations why we even have this mathematical framework. We also took a look at the definition and the properties of the joint CDF, and we mentioned that in contrast to the one-dimensional CDF, we usually don't estimate the joint CDF from data. It's mostly a mathematical tool that enables us to define things such as the joint density. And that's all I got. Thank you very much.